Okay, awesome. Well, thank you so much. As was said, my name is Dorota Grabowska. I'm not yet a professor. I have another month before that's an official title. But just a little bit of background on myself. I am a lattice field theorist by training, and I spent most of my life thinking about problems in particle and nuclear physics. This is also one of my first summer school lectures. So if I'm not explaining something carefully or well enough or confused, please interrupt me. The fault will be mine, not yours. So today I'm going to be doing the first section on quantum field theory. The second section will be done by Hank Lam on Wednesday. So also, I am not a condensed matter theorist, and so my lecture will unfortunately skew towards high energy physics. I will do my best to include some condensed matter aspects, but my knowledge base is more in high energy physics. It is also true that both high energy physics and condensed matter use quantum field theory, but they use them in different ways and with different goals. But we'll try and get at both of those in this lecture. But first, let me talk about quantum field theory, especially as contrasted with quantum mechanics. So if now after I'm about to use boards. No, I'll do it here. So let me first start with how I think about quantum mechanics and how that contrasts with quantum field theory. So quantum mechanics is the mathematical formulation that describes physics at short scales, but low velocities. And this was something that was started to be formulated in the early 1800s, early 1900s, and as sort of the fundamental aspects of quantum field theory, people took the Schrodinger equation and the Hamiltonian, equation and the Hamiltonian. And what I mean by this is essentially in order to solve a quantum mechanics problem, we generally just have to solve the equation I h bar dt phi is equal to h phi, where here's my Hamiltonian, here's my wave function, and my time evolution is encoded into this. So this is quantum mechanics. Now, if instead I think about quantum field theory, and this is where I'm definitely putting on my high energy physics hat, and you will shortly see my bias. So for me, if I think about quantum field theory, this is now the mathematical formulation that talks about physics at small scales again, but also high velocities. So really a relativistic theory. And now, instead of using the Schrodinger equation and the Hamiltonian, we instead use the path integral formulation and also the Lagrangian. And what I mean by this is essentially if I think about measuring some sort of correlation function to tell me something about my system, I'm going to measure the correlation function of the time-ordered product of operators, and this will be related somehow to the path integral formulation where I integrate over all fields with my operator, and then I have this I integral L normalized. And so now there's a couple of funky things about this way that yes. Oh, sorry. Please just raise your voice because I will not catch it.
Yeah, I was just going to say that you could, one way you could group, I guess you could just treat quantum mechanics as a 0 plus 1 dq.
Yep, that is exactly what I'm going to. Good. So there are a couple of funky things about the way that my high energy physics hat has phrased this problem, or in some sense this contrast, and it comes down to this. So, oh gosh. First of all, let me say why it's funky. So first, we know that there's a way to go between Lagrangian and Hamiltonian methods. This has been well known from classical field theory days. So in some sense, saying that one formulation naturally uses the Hamiltonian, the other uses the Lagrangian, is somewhat artificial. So in some sense, these two formulations can't be that different. The second is that condensed matter theory uses quantum field theory, And in that case, while they are in fact dealing with small scales, they're usually also dealing with systems that are non-relativistic. Relativistic. So in some sense, my insistence that quantum field theory is the thing that unifies small scales and high velocities is not in fact correct. So what gives? Well, in terms of justifying my own bias, part of the problem is that the way that I've been taught quantum field theory is based on historical developments, where, for example, Dirac, Heisenberg, Born, all of them were trying to understand how to create the quantum dynamics of electromagnetism, which is an inherently relativistic theory. So in some sense, the first quantum field theories that we have were, in fact, in this class. However, that is no longer true. So I think, as already mentioned, there is actually a much cleaner way to separate these two formulations, or perhaps more likely unify them. And that's in thinking that quantum mechanics is, in fact, as was mentioned, a 0 + 1 dimensional quantum field theory, where here is my spatial dimensions and here's my time. And now, on the other hand, a d + 1 dimensional quantum field theory can, in fact, simply be thought of as a many-body quantum mechanics. So in some sense, to complete the square, I can go here from, single particle quantum mechanics to many-body is just more particles. On the other side, to go from 0 + 1 dimensional QFT to d + 1, I just increase my dimensions. So in some sense, we really shouldn't be quantum field theory as being that different than quantum mechanics, just we have to be careful. So let me give a little bit more about this, because there are some key differences between quantum mechanics and quantum field theory will become important in how we think about formulating these theories on a lattice and also on a quantum computer. So for quantum mechanics, we essentially always quantize operators that do not depend on their spatial positions. And so what I mean by this is, for example, if I think about the quantum harmonic oscillator, I just have x squared plus p squared. If I think about the hydrogen atom, well, this is just minus h bar squared over 2 mu squared del squared minus e squared over r. If I want to get a bit more funky, I can think about including spin. And then this is just minus mu dot b. And this works great, as long as we're only wanting to describe one particle. So one of the key features of quantum mechanics is that there is no particle creation. And in some sense, this is sort of what got Dirac started on all of this, is that he wanted to be able to explain not only the spectrum of hydrogen, but how you actually went from hydrogen in an excited state, radiating off a photon and going down into a lower state. And this is where quantum field theory comes into play. So quantum field theory in this case, we now have to quantize operators that do actually depend on the spatial dimensions. And as a high-energy physicist, this automatically leads me to think about fields. So if I think about sort of the simplest Hamiltonian I can write down for a quantum field theory, though calling it simple, some would really disagree with me. Well, if I do it free, it's fine. I can write this Hamiltonian as operators that are conjugate pairs, but that now depend on the position. This is sort of the simplest quantum field theory Hamiltonian that I can write down. This will allow for multiple particles, and if I include interactions, I can also change the number of particles. However, this is not the only Hamiltonian that you could write down. For example, going to the condensed matter matter side, I could write down a Hamiltonian that doesn't really have these, what I would call fields, but instead is written as a spin chain. So this is the Heisenberg spin chain. Some coupling equals 1 to n of s n dot s n plus 1. Now this is also a quantum field theory because these operators depend on their position. So in both of these examples, either this free scalar theory from the quantum field theory perspective or this Heisenberg spin, both of these have some quantity that is getting pushed to be large, either particle number or operators or momentum, things of that sort. So in some sense, what I would say the sort of unifying idea behind a quantum field theory and why it's such both a rich subject matter and such a difficult one is that we have to deal with problems that involve a large, perhaps a macroscopic number of degrees of freedom that all interact with each other. And in some sense, this is really where all of the richness of quantum field theory comes into play. Now, it must be said that the reason why high-energy physicists and, condensed matter physicists use quantum field theory is different. So even though we might be using the same tools, our goals are different. So for high-energy physicists, we want to use QFT because it really is the one way that we know perhaps is a method for unifying quantum mechanics and special relativity. So in our trying to understand how particle physics works, trying to understand the fundamental nature of, well, let's say the universe, we're kind of automatically forced into quantum field theory. Is there a question? No? Okay. On the other hand, condensed matter physicists are not trying to understand sort of the fundamental nature of the universe, but are trying to understand the emergent phenomena that comes out of systems with many, many particles. So they're trying to essentially understand emergent phenomena. Of systems with many particles, and then use sort of quantum field theory methods to create effective descriptions. Effective low energy descriptions. So these are both ways of using quantum field theory that are slightly different from each other. However, they both use the same toolkit. In fact, both approaches rely really heavily on renormalization and renormalization group flow to understand how these theories behave at different energy scales, usually low energy and long distances. However, at the end of the day, the ultimate goal of both of these theories is to be able to match, and in a controllable way, our theoretical predictions to the physical reality around us, essentially using what method or operator that we want or can. And because in some there is that unified goal, we have seen a lot of interesting co-development between the two fields. For example, spontaneous symmetry breaking first emerged in the condensed matter side. We now use this to understand electroweak symmetry breaking and the Higgs. On a topic that's more near and dear to my heart, the way that we understand how to put light Dirac fermions on the lattice can be also used to understand how topological insulators work. So there's a lot of co-development that happens in both of these methods. So for the rest of the talk, I want to be talking about one of the ways that we think about quantum field theory, which is lattice field theory, but I will stop there to see if people have questions before I continue. Okay, so at the end of the day, this observation, where quantum mechanics and quantum field theory are not these dramatically different things, that there is this unified way of thinking about them, there is a mapping, there is in some sense a way of bringing them together, is really important. Okay, so with that, let me move on to lattice field theory. All right. Okay, so lattice field theory. The general idea here is that by implementing a theory on a discretized Euclidean lattice, we are able to non-perturbably regularize a quantum field theory. So said a bit more simply, by using a discretized spacetime, we are able to construct a fully well-defined quantum field theory, which is a really big problem if we're talking about Minkowski continuum theories. So the general idea is we have a non-perturbative regulator. And in some sense, all that we need to do is take our space-time, put down a series of points, and then implement our theory on this. Now, of course, that is much easier said than done. But let's just go with that for now. So I think about this discretized spacetime. I'm going to have space in this direction with some lattice spacing AS. My Euclidean time is going this direction, and I have some AT. And now I just need to take my quantum field theory and put it on this. And for simplicity, I'll mostly consider a hypercubic symmetry, where AT is equal to AS, but you can also deviate away from that. And the nice thing about this construction is that now the lattice spacing works as a UV regulator, and it provides a UV cutoff. Now, if we combine this with a path integral formulation, this lattice regularization provides a definition of the theory that is independent of perturbation theory. So for example, if you want to use dim-reg, that definition is only perturbative. You will never fully capture the full dynamics of the theory. The lattice lets you do that, assuming you are happy working with discretized spacetime and Euclidean spacetime. So the two big benefits, before I go into all of the challenges of doing this, are that through this method, where we have this rigorous, well-defined definition of a field theory, we can address fundamental questions about quantum field theories. Now, for example, one of my favorite questions to think about is whether chiral gauge theories are well-defined. And the answer is we actually don't know. Despite seeing beautiful empirical evidence about chiral gauge theories at the LHC, we actually do not know whether it's a well-defined quantum field theory because we only have dim-reg to regulate it. Now, the second nice thing about the lattice is that it allows for numerical simulations. And the nice thing about this is that we can actually take our lattice field theory, put it onto a computer, simulate it, and get some first principles understanding about strongly coupled physics. So for example, if I want to think about QCD in the low energy regime, our only first principles test, our only method for doing first principles studies is this lattice formulation. However, I would be remiss to not talk about some of the challenges. This is not something that can just be done without any sort of thinking about the ramifications of it. And so this is what I want to spend most of the rest of my talk talking about. So the challenges of working with a lattice field theory, and it might be that some of these can be rectified when thinking about, for example, a quantum simulation, is the first is that we've broken Euclidean rotational symmetry. So not only have I rotated into Euclidean spacetime, but now I've also broken rotational symmetry, which is sort of similar to breaking Lorentz invariance, which seems very, very bad because Lorentz invariance is such a sacred topic in quantum field theories. So in some sense, this breaking has to disappear in the continuum limit, and that has to be carefully understood. Now, the second thing, as I mentioned already multiple times, is we're working in Euclidean spacetime. So we're only calculating Euclidean correlation functions. Now, this can be tricky because you might think, okay, if I have a Euclidean correlation function, I can just analytically continue to Minkowski space and everything should be fine. However, this is, again, a hard thing to do. It's also not always clear that when you measure something in Euclidean spacetime, when you put a theory in Euclidean spacetime, that it has a clear correspondence to the Minkowski space theory of our world. So in some sense, you have to be careful about whether you can actually extract physical information from this. Now, the last thing comes when we're thinking about actually carrying out numerical simulations, and there's that we have to use finite volume, finite lattice spacing, and other such approximations, and therefore when we take the continuum limit, the infinite volume limit, we have to be sure that we're actually ending up at the theory that we wanted to reach. So these are kind of the three challenges that one needs to think about when formulating a lattice field theory. A lot of them have already been addressed, but some of them are still open questions. Okay, any questions on that before I get into more specifics? Yes?
If I'm given a continuum QFT, is there a way to tell whether I can put it on the lattice or not? Can I go please repeat the question?
Yeah. Okay, so the question was whether if I am given a continuum theory, whether I know if I can and how to put it onto the lattice. Is that correct?
Yeah, I've heard people say things like if there's a gravitational anomaly, then you cannot.
Yeah, good. Oh, I love that question. Yeah, so it is not always clear how to put a continuum theory onto the lattice. And in fact, there has been about 40 or 50 years of work trying to understand which theories can and cannot be mapped. Hold on, I also see a question in chat. Good, okay, so I see the other questions in chat. I will come back to them in a second. But yeah, so in some sense, being able to map a continuum field theory onto the lattice and being sure that you can then go back to the continuum theory is kind of trial and error. There are some ways of understanding whether it is possible or not, and I'll talk a little bit about them, but anomalies are notoriously painful for lattice theories because anomalies do not actually exist on the lattice. So there's a question in chat about what does well-defined mean in the context of QFTs, if QFTs are not mathematically well-defined in general. Good, so it's a bit of a circular thing. So what I want to get to is that quantum mechanics is well-defined, it's axiomatic, we understand everything about it, things are happy. If I take many-body quantum mechanics, things again are well-defined and happy, there's no issues. QFTs have all these infinities running around, so we have to somehow control them. And so for me, the way I think about well-defined is if I can write down a lattice description and have some sense of how to take the continuum limit, then that is well-defined. So for example, QCD with light quarks, I say is a well-defined field theory because I can write down a well-defined lattice field theory for it. Chiral gauge theories are not, at least not yet. Okay, the second question is there reason to discretize both spatial and time coordinates? Yes, because we don't want finite degrees of freedom to work on a computer. And also, if I just discretize space and not time, that kind of breaks the Lorentz invariance that's inherent to, or it's sort of the symmetry between space and time that's inherent to quantum field theories. Provide some quick examples of the three challenges. Yes, I will get to them, so stay patient. If by the end of the talk you still have questions, I'll come back to it. Okay, other questions from the audience, not from the chat. Yeah. So good, so the question about the number 3, the finite volume, finite lattice, whether there's an issue with periodic boundary conditions. Sometimes there is and sometimes there isn't. Let me give examples to define it. So if I think about a field theory that has a finite extent in its potential, then at some point, that theory stops seeing the boundaries, and so your continuum infinite volume theory is insensitive to those boundary conditions. So for example, QCD generally doesn't care about the boundary conditions. It's good to give them ones that kind of play well with the theory, but you don't have to. On the other hand, if you, for example, try to do QED in a finite box, there you have a long-range interaction, there you have Gauss's law, and implementing boundary conditions such that Gauss's law is protected is very difficult to do. There are methods to do it, but one has to be very careful about these finite volume boundary conditions for long-range theories. Okay, good. So let me go over here. So the idea for lattice QCD, lattice field theory, is that essentially we can determine everything about a quantum field theory from its time-ordered correlation function. So essentially, if I want to understand a QFT, I can try and measure this correlation function. And this can be defined as this. Xn. So essentially, this can tell me everything about a quantum field theory if I can somehow measure these correlation functions for any n that I want. So for example, this G of 2 is my propagator. And it'll, for example, have the form, it'll have a pole at k squared plus m squared plus I epsilon, where I'm using mostly plus. If I wanted, let's say, extract scattering information, then I might look at something like G4, x1, x2, x3, x4. So in some sense, measuring these correlation functions gives us scattering information, gives us particle masses, all of that. Now, if I use the path integral formulation, another way to write these correlation functions is in terms of, well, the path integral. So in this case, I have that Gn is now not defined as that correlation function, but is instead defined as this measure, e to the I Sm phi of x1, phi of xn, and normalize in a proper way. Where, for example, this action for a scalar theory will look like minus v phi. Now there's a couple, I'm missing a page. Good, and so we can do this is all done in Minkowski spacetime. Now, the problem with doing this is that because this object is highly oscillatory, it is not at all clear that we will get a well-defined happy field from this. Because it's highly oscillatory, and so it's not clear that this will actually give us a convergent integral. This is just something that is inherent to quantum field theories and working in Minkowski spacetime. So instead, what we can do is we can analytically continue and if we do so, what this does is that we essentially, because of this action, it now becomes not oscillatory but decaying, and therefore we get a well-defined field theory. Well, we get a convergent integral. So notice that nowhere in this have I actually made mention to the lattice, but even when doing run-of-the-mill quantum field theory, continuum quantum field theory, I already start analytically rotating into Euclidean spacetime. I'll come back to that question. So one way to see why this object becomes well-defined is if I think about what this field actually looks like. If I work in the Heisenberg picture, well, I now have, instead of an eye hanging out here, I instead have no eye. And so therefore, if H is bounded from from below, we can actually find that, for example, G2, and I'm not going to go through the math of this, can actually be written in Euclidean space as the sum over states e to the minus e n x4 e to the I p n dot x, where this is what will give us this nice convergent integral, because the hope is that as long as this doesn't grow too fast with energy, this decaying exponential will cut off the high energy modes. And so in some sense, this is why even in continuum field theory, we tend to go to Euclidean spacetime, because things make more sense there. Now, the claim of any lattice theory is that what we can do instead is not even analytically continue our correlation functions, but instead write down a Euclidean path integral, measure correlation functions, and those correlation functions will tell us something about the Minkowski theory itself. So let me write that in words, because that is one of the key statements of lattice field theory. So again, the idea here, let me get a bigger piece of chalk, is that if I take a Euclidean theory, measure a correlation function, then this tells us something about the Minkowski theory that we want. This step is incredibly non-trivial. Trying to prove that this holds has been done for some theories, but not all of them. And so in fact, we kind of know what theories these holds for. We know the properties that these Euclidean theories have to have. And this was shown in 75 by Osterwalder and Schrader, that if your Euclidean theory satisfies certain properties, then the correlation functions from that theory always correspond to the Minkowski theory correlation function. And the properties that Euclidean theory must have is that it's SO4 symmetric and translation invariant. That the correlation functions are symmetric. Ooh, sorry. And that the theory obeys something called reflection positivity. If you can show that your Euclidean theory satisfies this, then you know that you can use the Euclidean theory to understand the Minkowski theory. This is not always guaranteed, and in fact, some of the theories that we try and put on the lattice do not obey this. But in some sense, some of the theories that we do, for example, QCD, we can show that this holds, which is why we are comfortable using Euclidean lattice field theory. So to summarize about why I went on this formal aside, so the entire story about why we're okay working with Euclidean spacetime is that measuring Euclidean correlation functions for certain theories can tell us about our Minkowski universe. Now the question is how we actually do that, because even a Euclidean field theory still has divergences and infinities in it. So this is where the lattice comes in. We still need a UV regulator even in a Euclidean theory. And so this is where the lattice comes in, is because it gives us that UV regulator that allows us to control the infinities even in a Euclidean field theory. Okay, before I start talking about how to do this, I'll go for questions.
I mean, even if you know all the correlation functions in one vacuum, how would you know like monopole spectrum and things like that? Like motivated things that take you from one vacuum to the other vacuum.
Good. Yeah, so in some sense you're thinking about like different topological vacuums, right? So yeah, so you have to be careful about how you define it, but there are sort of ways to do this, because this is generally assumed that the vacuum contains all of the different topological vacuums, and you kind of average over them or include them. So you have to be careful when you're actually trying to do like transitions.
But it can be done.
Yeah, I mean, it's good. I mean, I think that, I mean, there's an entire thing about how topology doesn't exist on the lattice and topological freezing and things like that. But I think if you are careful in how you define it, we know how to define topological vacuum. And so you shouldn't be able to define it. I do not know how to do it off the top of my head. We can definitely look at it together. Yeah. So yeah, so reflection positivity is something about what the correlation functions have to obey, and it's something about how, if they're reflected in a certain way, that things are measured the same way. I don't want to go into great detail in it because it's a massive pain. So these two are kind of give-me's, easy to do and have. This one is insanely difficult to show and has only been shown to work for certain theories. Yeah? Yeah, so this is essentially that Gn of x1, x2, dot, 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 is Gn of x2, x1, dot, dot, dot. So they're symmetric, for bosonic theories, that they're symmetric under permutation. Exactly, yeah. So that sort of preserves the Wick rotation, the translation invariance, things like that. Yeah, exactly. So reflection positivity is related to unitarity on the Minkowski space, yeah. Yeah, so my goal in sort of all of this was not to give you a rigorous proof that we can always do Euclidean correlation functions, but just a sense of there is a way of understanding when we can use our Euclidean theories to understand something about our Minkowski universe. Because this is one of the things that often gets lobbed at lattice field theory is, well, you're working in Euclidean spacetime, so how do you know you're doing anything related to our universe? We have some mathematical proofs of how to do it. Okay, other questions?
Why would you want unitarity?
Why I want unitarity? So for me, unitarity is sort of a fundamental property of quantum field theories. In some sense, if I don't have unitarity, I don't know how to define my theory. Now, you can say, okay, well, maybe it's an effective field theory, and then I kind of lose unitarity.
Okay, I didn't want to difficult.
Yeah. I mean, it's a good question. In some sense, if I have like an effective field, I don't really care about unitarity, right? If I look at, for example, Fermi's effective theory for W scattering, right? That famously is not a unitary theory, but we know that's an effective field theory. If I actually want a field theory that sort of describes our universe, I think at the fundamental level I need unitarity. Okay. Is it possible to define a hyperbolic lattice structure? I am not sure I understand that question. So for me, this might not be what you're asking. This is from the Zoom chat. It's just something that has a hypercubic symmetry. So I literally just put down a 4-dimensional grid of equal spacing. That for me defines the hypercubic symmetry. Yeah.
Whether you use a classical formulation or not, is it completely case dependent?
For a quantum field theory? So if I want to put things on a computer, I need the lattice field theory description. as a high-energy physicist. Now, a condensed matter person might argue that, you can use the Hamiltonian formulation if you somehow figure out the low energy degrees of freedom, so on and so forth. But for me, if I want to do, for example, QCD from first principles, I integral formulation, and that's because of the way that we can actually simulate the theory I will get to. So if I don't address it by the end of the close to the end of the talk, ask me again. Okay. Good. Okay, so hopefully in all of that, I've at least given you hope that it is not necessarily a problem to work with Euclidean spacetime in order to understand our Minkowski universe. Now, the question is, now I still need to regulate it, so I need to put things on a lattice, and how do we actually do that? So let me go through how we actually put a field theory on a lattice and where all of the difficulty starts coming into play. And let me just erase the rest of these. Okay, so I'm going to start with a theory and put it on a lattice. And I'm going to start with either the simplest theory to put on the lattice or a theory that you should never put on the lattice, depending on who you want to ask. So I'm going to start off with the scalar theory. And so our goal is to go from our Euclidean formulation, continuum formulation, and map it onto a lattice. Now, the reason why I'm starting with this theory is because this is the theory where it is in some sense simplest to understand how to actually discretize spacetime and your fields. So in this case, I know what the Euclidean continuum theory is. It has this form. This is my path integral measure, e to the minus s of phi, where s of phi is positive and bounded from below, and it just looks like plus v of phi. And so all I have to do to put this on a lattice is understand how to write this in a lattice formulation, understand how to write this in a lattice formulation. That's all. It sounds simple. The first thing that we can sort of propose is that in this case, let me go up here, that my scalar fields are going to live on the lattice points. And now I say that we're just going to guess that this is the correct thing that happens and then see if we get a reasonable theory. So in this case, if I have my lattice, my fields live here, and dimensionally, that's sort of the easiest. And so I'm going to guess that the mapping from my continuous variable to my discretized ones, so each field will now, at a certain position x, will be mapped to a field at a specific space-time point. My integral gets mapped to a sum. And then if I have a action that only depends on the fields and not its derivatives, something like d4x m squared phi squared plus lambda squared phi to the fourth, well, this just becomes a sum over lattice points of ma over 2 squared phi n squared plus lambda phi n to the fourth. So that's kind of the obvious side of it. Now, the thing that I still have to do is how to treat that derivative up there. And in this case, we can think about different versions of discretized derivatives. So for example, I can take that a squared d mu phi maps to del mu squared phi n, which is defined as phi n plus mu minus phi n, where this is essentially a hop like this. I could take the negative version of it, or the inverse, where now it's phi n minus mu. Or I can take maybe some combination. And in some sense, a priori, there is no definite choice. You kind of just have to see what works. Now, in this case, for a scalar theory, we can just go with the simplest choice, in some sense because we hope that since the lattice is just a UV regularization method, as I go to the continuum, or as I extract physics from it, my continuum theory should not care about the nitty-gritty details of exactly how I did my discretization. My numerics might care, but my continuum theory, if I've correctly done things, if I have the correct, for lack of a better word, universality class, it doesn't care whether I pick this form, or this form. And so in some sense, we can just pick the simplest, and in this case, my d mu phi squared will now look like the sum over n and mu of, oh gosh, minus phi. Let me give myself a little bit more room. d4x phi squared will look like the sum over lattice points and directions of minus psi n plus mu plus n minus mu, and then minus 2 phi n. That's my discretized part of my action. I have assumed an infinite lattice or finite boundary condition, or periodic boundary conditions, which is totally fine for a scalar theory. Now, the last thing that we need to do, because so far we've only handled things in the action. If I'm thinking about a non-perturbative definition, I still need to handle the measure that appears in that action, that d phi. And the nice thing about working with a lattice field theory is that there is a really simple way to define the measure, which is simply as a sum or the product of integrals. So if I think about d phi in this case, then this is just the product over all positions, and you carry out an integral from minus infinity to infinity, d phi n. So for example, if I want to write down my Green's function for my continuum theory, I can map this into a lattice version where I have some normalizing factor, the product over sites of these integrals, minus infinity to infinity, e to the minus s lat, and then my operators. Now, S lat is at least binomial, positive definite, so that decays away. This is positive definite. I can do all of these integrals, and now especially if I have a finite volume where I have a finite number of lattice sites, this is a well-defined integral that I can do, or multi-variable integral that I can do. There are no infinities running around. This is what the lattice gives you. Finite volume, finite lattice spacing. For a scalar theory, this integral is well-defined, convergent, no infinities. It is UV regulated. Does that make sense? Yeah?
So if I put m squared to be negative for SSB, I can see that there's a tachyon reflection.
Yeah, I would. Sorry. I'm really bad at that. So the question was, if I flip the sign of m, for example, to have spontaneous symmetry breaking, then I would see a tachyon taking form. Yeah. Exactly. So the sign of m does, in fact, matter. Other questions? How do you define the derivatives in higher spatial dimensions? Good, that is a great question. So I do it the exact same way. So this mu right here is a sum over all directions. So because I'm on a hypercubic lattice, essentially from any point, let me do a two-dimensional one. I derive derivatives going this way, and then also going this way. And then there's the obvious three-dimensional definition. So it's a simple generalization to higher dimensions. Okay. Good. Now, the important thing about this, and I've mentioned already briefly the continuum limit, is that this sort of goes to is not that, this is not defined as an equality, but in some sense a mapping. And the reason why I'm sort of saying this is a mapping on a definition is that we somehow need to take the continuum limit. So, yeah. Yeah. No, sorry, that was good. So yeah, so the key thing about this is now I have everything as sort of well-defined, consistent, but at the end of the day, I want to somehow take the continuum limit, and the issue is that it's not quite clear how to do this. So once we have essentially regularized, it is not a priori clear how to take the continuum limit. And this is kind of the nut and bolts of how to understand quantum field theories, is that I can write down a well-defined lattice field theory, but I have not yet proven that it maps to the continuum theory that I want. And this is, for example, why the Millennium Prize for proving that Yang-Mills has a mass gap still exists, because no one's proven the continuum limit for Yang-Mills. And so essentially, if I measure, let's say this, on a computer, I have some G that's measured at a finite A, and it is not clear how to change the parameters in this lattice action, how to take A small, how to change the volume, such that I end up mapping to G A equals 0 in the universality class that I want. So essentially, care must be used when taking the continuum limit to try and ensure that you end up with the correct continuum theory. Now, the nice thing is that in the theory that's of most interest to high-energy physicists, QCD, we actually know how to take that continuum limit. We know that due to asymptotic freedom. We know in some sense the direction of the continuum limit. Now, for non-asymptotic free theories, like phi to the fourth, it's not clear how to take the continuum limit. So in some sense, you might say, I've written down a lattice theory, I can measure something in it, and now I know something about the universe, and you could be simulating the wrong theory. This is why lattice is hard. All right, questions? Yeah? Mm-hmm. Yeah, good. So I have been a little bit quick. So let me, yeah, I'm sorry. You're going to have to keep reminding me to do that. One day I'll get it. So the question was, can I talk about how to take the different continuum limits and what exactly that means? Good. So let me start over here where I have this action, right? So in some sense, when I've written down my action over here, I have this parameters m, oh God, and this parameter lambda. So when I carry out a lattice simulation, I have to tell my computer, hey, I want m to be this value, hey, I want lambda to be this value for this given lattice spacing and volume size. And now I want to go closer to the continuum, so I have to change A. Well, I know that A is my UV scale, and I know from perturbative physics that every time I change my UV scale, my couplings start running. So I have to figure out, okay, well, let me change m in this way, let me change lambda in this way. Is that the direction of the continuum limit? So in some sense, I can think about the continuum limit as how I tune the mass and the couplings. The reason why this is kind of known for an asymptotically free theory is we know which direction the gauge coupling runs at high energies. We know how the mass runs as well. For non-asymptotically free theories, we don't know. And in fact, a lot of the work that goes into simulating QCD, real world vector QCD, is saying, I'm working at this lattice spacing with these number of lattice points. I want 140 MeV pion. What do I tune the quark masses to? Good. Does that explain it? Excellent. Yeah. Yeah, yeah.
So you said I have a bunch of choices in how I discretize it as either phi m plus b minus
Yeah.
phi m minus phi m minus 2. And then I think you said that the simplest choice was to take the sum of the two opposite sides and subtract one at the side.
No, so essentially, so you can, essentially, there's, the simplest choice are all, no, let me rephrase that. Essentially, any choice you make is the simplest one. So if you take, let's say, you say, you know what, I like plus signs. I don't know why I like plus signs. And I do del squared phi and square it, I'll get this. Now, if someone else says, you know what, I like negative signs, and they do the exact same thing, they'll get that same answer. So in some sense, the reason why I say that this is simple is because it's just nearest neighbor. But for the scalar theory, it doesn't actually matter which one you choose. You always get your second derivative looking like this, and it doesn't change the physics in any way, shape, or form.
So the second derivative, regardless of I just always contains both terms.
Yeah, exactly. Yeah. Remember this when we talk about fermions. Yeah. Oh my gosh. I'm sorry, guys. Sorry to everyone on Zoom that I'm so bad at this. The question was, I said choose making the simplest choice about which form of the first derivative I choose, and the question was, how do I define the first derivative, or how do I define the simplest one? And the answer is it doesn't really matter because you'll always get this version. Okay, I saw another question. I will repeat it this time.
So you're taking the lattice spacing to 0, you're also increasing the number of lattice sides to infinity. Do those two limits commute?
Good. So the question was, thank you. The question was, I have to take both the continuum limit, so a to 0. I have to take the volume, also goes to infinity. Do those two limits commute? The answer is you have to be careful. So I know that is not the answer to your question. Sometimes you have to take both kind of at the same time, right? So imagine, so the volume is really the number of lattice points. So if I keep the number of lattice points fixed, but I take A to be smaller and smaller, eventually my physical volume is smaller than the radius of the proton, at which point, it's a bad description. Now, if I take infinite volume while my lattice spacing is kept fixed, well, then you just have a bunch of empty space, and you're going to have really, really bad numerics. Because in some sense, your proton is over here, but you're simulating everything over here where it's just empty space because things confine. So you do actually have to take the limit kind of simultaneously. Okay. Excellent. Good. I do want to make one statement about the continuum limit that is sort of related to the condensed matter side. So when we think about the continuum limit, what we're really saying is I want to find a set of parameters. I want to find a set of parameters, let's say m and lambda, such that as I take a towards 0, my result does not depend on my lattice spacing. Now, this is sort of the idea that is always around renormalization, so on and so forth, is that your physical results should not care exactly about how you've regularized the theory. If you've done it carefully enough, if you've done it correctly, it should not care. So in some sense, taking the continuum limit of a lattice field theory is equivalent to finding the critical points where your correlation length goes to infinity. As in, you become insensitive to the exact way that you've discretized the field theory. So this is this sort of idea of critical points or critical manifolds is where we get the tie into universality classes and condensed matter. So this is why both condensed matter physicists and lattice field theorists think about critical phenomena. Okay, and I'm rushing with it because I'm running out of time. Okay, so to summarize so far, because I know I've thrown a lot of you guys in a short amount of time. So far what I've discussed. So in appropriately defined cases, we can use the measurements from Euclidean correlation functions to understand something about our physical Minkowski universe. If we put that Euclidean field theory on a lattice, that theory is non-perturbatively regularized. It is a well-defined field theory. Continuum limits are hard, which is why I'm glossing over them, but we essentially know what to do in theory. In practice is difficult. Okay, but with that, Hank would argue I should not even be talking about continuum limits with phi to the fourth. Let me go to more physically relevant theories. So let me talk about how to do gauge theories and fermions. And I will fit this in the next 25 minutes. Okay. Any last questions before I move on to gauge theories and fermions? Yeah. Yeah, so good. So I guess what I'm trying to get at is that in some sense, condensed matter physicists think about sort of criticality and universality classes in trying to write down microscopic descriptions of macroscopic phenomena. And my understanding as someone who's not a condensed matter physicist is that essentially you work hard to come up with a theory that doesn't care exactly about how you've constructed the macroscopics, but gives you the low-lying behaviors. So again, it becomes insensitive to the sort of short-range interactions, but you've adequately described the long-range interactions. So it becomes insensitive to what happens at short scales. For a lattice field theorist to go to the continuum limit, you have to do the same thing, where you're no longer caring about exactly how that lattice spacing is defined. You're not really caring exactly what the interactions are, but your low energy, long wavelength theory is, for example, QCD. This is kind of how I understand it. Ask me again, I'll talk more about it, because again, not a condensed matter physicist. Yeah? Okay, so the question was, am I talking about a effective field theory universality class versus something like conformal field theory universality class? Oh boy. So I would think, and someone can correct me if I understand incorrectly, that condensed matter physicists would think about the effective field theory universality class. A lattice field theorist would care about the sort of not EFT, but an actual honest-to-goodness theory universality class, right? So for example, if I think about QCD, I know what the continuum limit is. It's Yang-Mills plus fermions. I don't want an EFT description. I actually want to map into that universality class. Okay. Good. Oh, goodness. Okay. So let me get to gauge theories and fermions.
Can I just suggest that there will be a discussion session after 5? So unless you have a question that related to what she's talking about, let's postpone it unless otherwise she cannot finish.
Yeah, I know. I prepared a lot. Okay. Get it all in though. So gauge theories. I feel like I'm missing my first page here, though. I totally am. Okay. So now the motivation here is, again, so we want to now actually, let's say, talk about QCD, which is a gauge theory. And the action, and because I do not have the page of notes on this, I'm going to be bad with my signs, but essentially my action is going to be d4x, and I have a q d slash plus m q minus, I think like that, f mu nu. And let me double check that I actually don't have this page, because I had some notes on it. And I don't. Okay. Good. So, oh, no, it's right there. Excellent. There is a trace here. Okay, so this is my continuum Euclidean action. So these are my quark fields. This is my covariant derivative. The covariant derivative is defined as my partial minus IG A mu, where G is this coupling constant. A mu is a matrix gauge field, namely A mu is A mu A T A, where I'm summing over gauge indices, generator indices. This is my generators. And this is my field strength tensor defined as I over G d mu d nu. So this is the continuum theory of QCD, which is what we want to get to. Now, I'm going to first focus on the gauge fields, so what's sort of encoded in this and in this. And then I will come back to the fermions, because the fermions have some really meaty parts to them. Okay. So, and because I want to put aside the fermions for now, let me instead write down the action for a scalar that's been gauged, just because it's a little bit easier to see how the gauge fields emerge in a lattice formulation. So in that case, my theory just looks like this. Phi dagger phi. Okay, so now recall from the discretization we had talked about before, my scalar fields live on links. No, sorry, live on sites. And now, if I think about how these transform, well, in the continuum, phi of x gets transformed by some field like this. So notice that this is my gauge transformation. Notice that this is completely local. Now, what this means, if I think about, again, this scalar field now living on the sites, I go into a lattice version, and so what happens is that phi of n now gauge transforms again as some v of n, phi of n, where both of these vn's, or x's, depending on how you want to think about it, are elements of your Lie group. So in some sense, a gauge transformation on a scalar field is always completely local. Now, if we think about what this means, if I, for example, look at this point here, well, this is just phi n dagger phi n, and it is true that if I look at this gauge transform, vn dagger vn is just equal to 1. So this is a gauge invariant object. Now, if I instead look at the derivative, so recall from, oh, it's actually still up there. If I discretize the derivatives, I now tie together different sites, right? d mu phi contains a term that goes like phi n minus mu. And now if I do a gauge transform on these, this will go, I should probably have a dagger on one of these, phi n dagger vn dagger, but vn minus mu, vn minus u, this is no longer a gauge invariant object. And so in some sense, one of the difficulties that arises when carrying out a lattice field theory with gauge interactions is that gauge transforms act locally in a continuous way, but now I've discretized things. And so instead, what we have to do is we have to define a new type of variable that only exists sort of in the lattice theory that can take care of, in some sense, parallel transporting the gauge transformation from one site onto another site. So to give you a picture of what that means, if I think about my lattice field theory, if I have a field here and a field here, and I do gauge transformations, I need a gauge transformation transporter that transports my gauge transformation from one site to another. And this is what we call our gauge link. Do I have it written down? So this is where my gauge field lives. You can think about a gauge link as essentially related to a Wilson line, which is some path-ordered exponential of my gauge field dotted to some line index. So there's a couple key features about this. The first is when I think about my continuum theory over here, this A mu is a local field, and it lives in the Lie algebra. Now, when I go into a lattice field theory, my U carries two indices, its starting point and the direction that it goes. So it's now not a purely local object, but a sort of nearest neighbor object. And it also lives in the Lie group of my theory. However, once I have this, I now know how to easily write down this sort of interaction. And in fact, in this case, d mu phi dagger, d mu phi, now is simply written as the sum over links, 8 phi n dagger phi n, which is gauge invariant, but then I have another sum over sites and directions, phi dagger n. I put in this gauge link in between to parallel transport my gauge transformation from one site to the other, and then the corresponding converse one. So this is one of the first places that we see really non-trivial behavior for a field theory on the lattice, is that now, whereas before I had gauge fields that were living in the Lie algebra and were completely local, I now have my gauge fields are encoded into something that lives in the Lie group of my gauge symmetry, and is also not fully local, but in fact lives on the links that connect the sites. Does that make sense? I know that I'm going quick at this point. Okay. In the continuum limit, the kinetic term is also not invariant under gauge transformations. Why can't we just adjust the gauge field to swallow the term in the discretized version as well? Yeah, so the swallowing of that gauge transformation, so in order to write that covariant derivative, is exactly what the gauge link does. So in some sense, the exact same thing that you do in the continuum where you write a covariant derivative, you do the same thing on the lattice. Yes? It's an 8. That one? Yeah, okay, that was just a messy 8. Yeah. Okay. Now the other thing that we need to do when we take into account gauge fields, we got to do the gauge action. And now I know I'm going very quick. So we have to somehow write this f mu nu as something. And this is where we get what are called plaquettes. And so now this object is not even a link. A plaquette is simply made out of connecting 4 links going from nearest neighbor into a square. And we can use this to actually construct our action. Okay. Now the last thing, because I did really want to get to fermions. So essentially, when I think about doing gauge in a lattice field theory, my gauge fields have to live in the links because they are essentially the transporters of gauge transformations in my field theory. Okay, so let me quickly try fermions. So if you recall, there was a question about how to do the derivatives in a scalar theory. And I also said that essentially the continuum theory would be insensitive to how you discretized your derivatives. And that's true for the scalar theory. Fermions, that is no longer true. In fact, you have to be very careful how you define your fermionic action in order to not get what are called doublers. So let me quickly do a free fermion. So my Euclidean action is minus the integral over x of psi bar d mu plus m psi, where now these are Grassmann variables, and I have to think carefully about how to do that d mu. So again, I can go through essentially all that I did with the scalar theory and see what happens. So in this case, I take my continuum Grassmann variable, I map it to a site one, and I do the same corresponding one for psi dagger, and now my derivative, I can again go to the forward one, the backward one, or a mix of the two. Now, in the case of the scalar theory, because I had a second derivative, it did not matter which one I used. However, notice that in this case, I only have a first derivative, and I don't have hermiticity properties if I use either this version or this version. In some sense, we know that d mu is anti-Hermitian, but you can work through it and show that d mu dagger, the forward derivative, if I dagger this, this goes into d mu minus. So these do not have definite hermiticity, and therefore if I use either one of them for my discretized fermionic action, I do not get a well Lagrangian. Again, I get a sort of Hermitian theory. Therefore, I am stuck using this one, which you say, okay, that's reasonable. We can use that one. We can see what happens. So in that case, let me say that because of that, my fermionic action will read as minus s summing over lattice sites and direction, psi bar n, gamma mu, and then I have a forward derivative and a backward derivative over 2 plus my mass term. And you can say, okay, well, that still looks fine. I see nothing wrong. So let me now go into, do a first transform, go into momentum space. So essentially, psi n will be an integral over k, e to the I k n psi of k, and k e to the minus I k n psi. Okay, and then plug both of these into that. And what I find if I go through the algebra, what you'll find is that your action, now written in momentum space, is given by psi of k I sine of k mu gamma mu plus m naught psi. which means that your propagator, your G2, written, again, using momentum, goes like NP. It's like 1 over I sine of k mu gamma mu plus m naught. And this is what I wanted to get to. So what does this tell us? So remember that the propagator tells you where you have poles. They tell you the mass of your particle. So I wrote down the theory up there for a single massive Dirac fermion. I should expect that this will give me a mass of a single Dirac fermion. And so you can say, okay, well, I think it does. And so one way to see that is you can take this k mu and m naught, write it in terms of lattice spacings, and then take the continuum limit. So if I define k mu as k bar mu a, where this is dimensionless, this is dimension full, m naught is m bar a, and expand around 0, I see that I have a pole. I find that this propagator goes like 1 over a I k slash plus m, which looks like a fermionic propagator with a pole at k squared is equal to minus m squared. So that seems fine until we take a closer look. So now let me look at that sine k mu again. Now notice that there's actually 3 different places where that sine k mu is equal to 0. So this is my sine k mu. It is in fact a sine function with zeros at 0, but also at minus pi to pi. And remember that in a lattice theory, for example, if you think about a condensed matter system with like a Brillouin zone, your maximum momentum for a lattice spacing goes like pi over a, physical. So when I do this integral up here over k, that goes from minus pi to pi. And so in fact, you pick up this additional poles, because that sine k mu has additional zeros. Now what this means is that you don't only have a pole at k equals 0, but you also have a pole at k equals pi, and also then minus pi. So essentially what we find is that we get poles which correspond to the degrees of freedom that we'll see in the continuum limit. We get poles at k mu is equal to 0, but also at pi for every mu direction. So what this means, if you're doing a 4D theory, you have 4 different mu directions, and therefore you will actually have 2 to the 4 poles, if m goes to 0 especially. And this is the origin of the fermion doubling problem. It is the fact that from using this first derivative, we get additional poles if we use that naive discretization. Does that make sense? I know I'm really rushing through it. Yeah. So essentially, if I take a look at this, let me just look at this sign. It's the fact that essentially what I'm trying to do is expand around sort of let me try that one more time. So if I plug this in, and I keep k mu and m fixed, a goes small, and therefore this sine of k mu, which is sine of k mu a, this is fixed, this is small. I can write this as essentially k bar a in the small a limit. So essentially that sign becomes ka, becomes linear. Now, the issue is that I can do the exact same thing if I expand sine of x around x is equal to pi. I also get this small angle, or I also get sort of linear Taylor series. So essentially, what I'm saying is that if I just plot sine k, there are 3 zeros. There's one at 0 and at pi. So if I take the continuum limit, I don't get just one fermion. I get multiple. So it's identified. So yeah. Yeah, the question was just a re-explanation of how that works. So essentially, by choosing, in some sense, this naive action, where I said, it shouldn't matter what you do, you can just sort of do the naive action, I actually get multiple fermions, much more than I wanted to. And so in some sense, in this case, you have to be very careful about the sort of fermion action that you write down. And this I absolutely will not have time to go into. But we know how to solve this problem. We know how to solve the fermion doubling problem. It's a really beautiful story involving chiral symmetry, anomalies, extra dimensions, and also why we still don't know whether chiral gauge theories exist or are well-defined. Leave that for another day, and I'll end there, and I'll let Hank finish Wednesday.
Okay, if there are other questions, we already had plenty, but maybe we can keep them for the discussion session. Let me just say, you said you're not a professor, but I should contradict you. That was a beautiful lesson.
Thank you. Yeah. Yeah. Sorry, you mean, oof. Here? Yeah, so it's the sense of if you have a finite spatial extent, right, that naturally cuts off your maximum k value. So if you have a box of size A, then the maximum mode that you can fit into it is pi over A. So this is kind of like if you've done like Brillouin zone or things like that, it's exactly that. Yeah, so I went from position to momentum. So I can define a field theory either in position or momentum space. So they're just related by Fourier transforms. Oh, you mean when it's in sort of it's a simplified way. Yeah, sorry about that. This is just defined as d4x. It just saves me some writing, but I should have made it clear. Other questions? I know that was a lot. All right, well, I'll also be around until Thursday morning, so feel free to bug me, especially if you want to talk about chiral gauge theories and anomalies.
Great, so we meet back here at 1:45. Little break.